Here's my wave tank at school. We have a little bit of water in here. You can do the same thing at home with a clear glass baking tray. I have a flashlight up above that'll shine the light down through. Now with the lights out, we can see that when I make a wave, it creates bright and dark regions below. The bright are the crests of the water, and the dark are the troughs. We'll start with reflection. I have a barrier in the water, and this is going to represent a straight line wave generator. You can see the reflections. Now we can see the wave shadows. They're reflecting off of the barrier. If I change the angle, we get a different reflection. Now we have reflection along what's called a concave reflector. Can you see the reflection coming to a focus? Now we have a convex reflector. Can you see that the waves are spreading out after reflecting? This is called diverging. With the concave, it was converging. Now we're going to see what happens when waves pass through an opening in the barrier. Do you notice how they're curving as they pass through just on the edges? Now we're going to reduce the size of the opening. Wow, that's a lot of curvature on the other side. When waves pass through an opening in a barrier, it's called diffraction. The curving of the wave as it passes through. Waves curve more when the opening is small. I've lowered one corner now, and I have a deep end and a shallow end, and there's the beach. Let's see what happens when the waves approach the beach. Now this might be a little hard to see, but the waves slow down as they approach the beach. Now when I change the angle, let's see what happens. They're approaching the beach at an angle. Can you see them swivel and curve around? The waves bend toward the beach. This is called refraction, the bending of a wave due to a change in speed. Now we're going to measure the speed of the waves. I have a meter stick. I've got the weight marking 30. I have another weight marking 60. You should be able to play this back in slow motion and get the velocity. You're going to need that velocity for the next part. Now I've got the wave generator creating these ripples at 12 cycles a second. I've just turned it down to 6 cycles a second. The speed of the waves is the same, but the wavelength is longer because the frequency is lower. Now we can see the waves moving out through the shadows. It's 6 cycles a second. You can check the velocity. You can even measure the wavelength now. If you know the frequency is 6 cycles per second, and you know the velocity, you can calculate the wavelength. And then freeze frame this and see if you're right. You can just look at the meter stick. And now we're at 12 cycles a second. Does it work? And just for fun, we have it going at 30 cycles a second. I'm going to shoot more of that. Now you can see if I put my hands in here, the waves just pass right through each other like we learned earlier. Now I have a second ball in the water, and we have 2 point sources. And this is what we get. Can you see the interference pattern forming? Crests from one match up with crests from the other. Troughs from one match up with troughs from the other. Where the crests and the troughs overlap, we get cancellations. These are called nodal lines. Where the crests meet up with crests and the trough meet up with troughs, we have maximum lines. We're going to mark the center of each source and then measure the distance between them. The distance between the sources is 18 centimeters. The center line is the principal maximum. Now there's a first maximum to the right. All right, they're supposed to be the same angle apart, but there's one on the left and one on the right. And there's a second maximum. Let's measure the angles. So we have about 10 and then 20 degrees to the first and then second maximum. We're at 12 cycles a second. You should be able to calculate the wavelength from the formula for interference, and then compare that wavelength to what you measured in the last section. Good luck, everybody.